Hi, everyone, and thank you for joining us for today's webinar. My name is Jonathan Hill. I'm an engineer here at ATA Engineering's Northern Virginia office. And in just a second, I'll be handing things over to Tommy in San Diego for our feature presentation, which today is checking element quality in Femap. Now, before we get that far, I have a few quick notes. The first of which is that today's presentation will be recorded, and probably tomorrow we'll have that recording available on both our software website as well as our YouTube page. So I'd invite you to check back at that time to rewatch the presentation or share it with a colleague. In addition, everyone's been muted for now. That's just so that we don't have any interruptions during the presentation, but there will be a question and answer session once we get to the end. And at that time, we'll share instructions on how you can unmute yourself. You're also certainly welcome to submit questions at any point during the presentation. Just note that we'll probably, or through the chat, just note that we'll probably wait to come back to those questions until the end as well. So starting off just with a quick overview of ATA. ATA is well known as a provider of high-value engineering services where we have expertise in design, analysis, and test. And we're really excited to help our customers overcome product design challenges across a wide range of industries, just some of which are shown here. In addition, we're able to leverage that expertise through our role as a partner and value-added reseller for Siemens software, where we support a number of product lines, including Femap and Simcenter Nastran, which we'll be discussing more today, but also others like NX, SimCenter 3D, Star CCM Plus, and more. We host a technical support hotline that runs from the beginning of the day on the East Coast to the end of the day on the West Coast, and that can be reached by phone and through our software website. And in addition, I always like to share that we are that we develop the official SimCenter Nastran training materials and are the preferred provider of SimCenter Nastran training in North America. Finally, the last thing I want to do is invite you to check out our software website after today's presentation wraps up. We have a lot of great stuff on here. We have our future training class schedule, as well as upcoming webinars. Probably my favorite part is the free resources section. So you can come here and check out a number of really great resources, APIs, white papers, on-demand webinars, things like that. So again, I'd invite you to check that out after today's presentation. But other than that, Tommy, it's all yours.
I'll go ahead and get started with an overview. So I guess the motivation behind understanding element quality is that element quality impacts model accuracy and then therefore result. And so you probably already know that finite element models already have some error because we're using finite discrete element shapes to represent continuum bodies. So a perfect element would be like an equilateral shape, so like a square or an equilateral triangle, etc. So the farther you deviate from that equilateral shape, the worse the element will be, and the less accurate your model will be. So in today's webinar, we'll go over what do these bad elements look like, how to identify them in Femap, how to improve them in Femap, and then at the end, I'll give a quick demonstration in Femap. And I'll be using the version 2019.1, but I've done similar stuff in Femap 11 and Femap 12. So for the most part, these commands are pretty similar across versions, but there might be slight differences. Let us know if you run into any issues. So here are some of the different categories of poor elements. The first one is aspect ratio. It's pretty straightforward. Essentially, one dimension is much longer than the other. Taper, kind of similar idea, but kind of narrows down as you go along the length. Warping is actually out of plane deviation. So for a quad element, you ideally want to stay in one plane. But if you start to kind of pull on it through in or out of the page and get like a third dimension, that's going to be an issue. And then, so these perfect element shapes also have equal angles. So for a quad, it'd be 90 degrees, for a triangle, 60, and so on. So you also want to make sure that your angles are as close as you can get to those perfect values. The farther away you get, either larger or smaller from those equal angle values, you'll get a bad element. And then kind of similarly, the skew looks like a parallelogram shape where they kind of stretch it out diagonally, and that's kind of also related to those large or small interior angles. And then Jacobian is interesting because in Nastran, the solution will actually fail if the Jacobian values are negative. All the other different kinds of bad elements, the model will still usually run, it just won't be as accurate, but Jacobian, if it's really bad, will actually error out. So one way to check your element quality in Femap is simply go to Tools, check Element Quality, and then select all the elements that you want to evaluate. There's two tabs in this dialog box. There's the Femap tab and the Nastran tab. If you're solving your model in Nastran, you most probably want to use the Nastran tab, but they're both helpful. And then you can also go in and change these values too. I mean, these are the default values, but if you have your own specific company or project requirement levels, you can edit those values as you need to. And then another method is in the meshing toolbox, there's a surface mesh quality section where you can flip through individual quality types like aspect ratio, interior angle, et cetera. And then for each of those individual types, you can look at element contours. And so outside of Femap, you can also look at the FO6 file if you're using Nastran. So if you run a Nastran file, you'll get a series of files like FO6, FO4, OP2, et cetera. The FO6 file will list out all the elements that Nastran flagged as poor elements, and it'll tell you which checks, what values they are in each different check type and where they failed. And just note that sometimes Nastran will flag elements that the preprocessor didn't, and vice versa. And if you have a lot of bad elements, I think the default in Nastran is like 100 or 200 that'll write out to FO6. And so if you get 100, you might actually have a lot more than that. So you should, if you have a large model with a lot of potentially bad elements, you could update the geometric mesh limit line to be a larger value to see all your bad elements. And if you're getting over 1,000 bad elements, probably means that either you have really complicated geometry or trying to mesh, or you might want to rethink your overall meshing strategy. So another way to do this, and this is kind of similar, we're looking at the FO6 file. We have the tool API program that actually reads that FO6 file for you, and it will create a group automatically of all the elements that were flagged in Femap. And you can find this tool on our PLM website listed there. Just click download the Femap API and then save the executable into your local Femap installation directory. And I'll show you that in the demo to kind of clarify that. So once you identify your bad elements and you made a group of them, you can kind of visually understand why they're there and how you might improve them. So as a general kind of rule of thumb, bad geometry often leads to bad elements. So if you have super complicated geometry or a lot of tiny sliver faces and stuff like that, that might be something to address from the start. And there's just a lot of things you can try. Like maybe you want to use a finer mesh, free versus matte meshing. If you have a nice even rectangular region, it's good to do a matte mesh to get really good elements in there. But if you don't have that, if you have kind of a more complicated curving tapered region and you try to force a matte mesh through that, you might get bad elements. So you kind of have to understand your geometry and whether it's better suited to a matte mesh or a free mesh, and do that accordingly. And kind of related to matte meshing, if you can, it's good to kind of divide your part into geometric partitions to kind of help maximize how much of it you can matte mesh, so like dividing the face or splitting body when appropriate. And the meshing toolbox in general has a lot of different options for fixing bad elements or kind of improving your overall meshing algorithm. Here's on the right is a screenshot of the mesh surface section within the meshing toolbox. So here have a bunch of options like the mesh size, free versus matte mesh, max quads, adding layers, surface growth, and even some advanced options like matte meshing options and stuff like that, smoothing. So these are all different tools you have available to you. And then there's also manual meshing, which is helpful if you don't have any underlying geometry, you just have elements and nodes. These are some ways you can fix bad elements, and I'll go through that in more detail on the next slide and in the demo. And then if you're doing a solid mesh like a TET mesh or a brick mesh, it's often helpful to start off by seeding your some of the faces with 2D elements first. That'll kind of help the 3D mesh do a better job. And especially if you have like small fillets or really kind of curved surfaces that are a little bit tricky, if you use a 2D seed mesh first, that'll often help. And also kind of one step further, if you do that, it's helpful to also check the element quality of the 2D seed elements too, because even if your solid elements pass the checks, if your seed elements don't pass, that might still mean that you have some questionable elements. So to really get a really good solid mesh, it's helpful to use seeds and check those seeds. And then lastly, for a large model, like a big assembly or something like that, if you have dozens or even hundreds of components, I find it easier to check each part mesh separately and then move on to the next one instead of having to try to look at the entire assembly mesh at once and fix everything all together. So more details about the manual meshing. So again, this is helpful if you have no geometry underneath your mesh. So there's two categories here. There's the mesh editing and the mesh remesh. So in mesh editing, you're looking at individual elements. Maybe you want to split them. So like, for example, this top dialog box, this has a very high aspect ratio kind of element. If you have something like that, you may consider trying to split that into multiple smaller elements to improve the aspect ratio. But just kind of a caution is that if you do use that method, make sure your mesh is still connected afterwards. Sometimes you're going to be introducing new nodes into the mesh, which might not be connected to other nodes. So just be careful for using these tools. They're helpful, but make sure you understand how they kind of change what your mesh looks like. And then the second category is the mesh remesh. So here, similar idea, but instead of editing single elements, you're editing a group of elements. So if you have like, let's say if you have like a bunch of bad elements in one, kind of localized to one spot, and you don't have any geometry to fix or update, you can grab that group of maybe 25 elements and say, I want to remesh or refine these elements. You can just click and drag on the screen or create a group of those elements, and then you have a couple options like refining them or even making them less refined if that's what you want to do. There's some good options to have. And then now I'll go ahead and jump into the demo. So some of you might recognize this model. It's similar to the one we used in the previous demo, the Meshing Toolbox webinar. In that webinar, we focused primarily on geometry, the geometry preparation for meshing and things like mid-surfacing and editing features and things like that, and geometry-based mesh updates. Today, we'll kind of focus on the opposite. We have a mesh already. How can we evaluate it and improve it, especially if you look at this model, there's actually no geometry. This is an imported Nastran deck. So we'll go look at some of those methods that we can improve the mesh without having geometry underneath it. So the first thing I'll do is demonstrate the Femap API tool. So I went ahead and downloaded that API and saved the executable file into my local installation. So if you want to see where that is under tools directory, usually for me it's C, Siemens, and then under that version API folder, you just copy in here with all the other custom tools. And you can put it somewhere else if you want. That's where I have it in here. So if you go ahead and run that API, it'll prompt you for an FO6 file. So I happen to know that this one corresponds to my model, but you want to double check that you're selecting the right FO6 file. Click OK. And then so it created 6 elements. So it says that there's 6 bad elements according to the FO6 Nastran file. So it creates the group of those elements here, can visualize those. And then we can even open the FO6 file ourselves just to kind of confirm. So here's the very same FO6 file. Here are the 6 elements. So that kind of, and then we can see why they failed. So these 4 X's mark that these 4 elements failed the maximum interior angle check, and then these 2 were because of taper ratio. And then another method of checking element quality, like I mentioned, was tools, check element quality. And so we will select all. I guess I prefer using the API just for the beginning because maybe it's fewer button clicks, but whichever way you prefer works. Ideally, they give you the same result. So if you're using Nastran, let's check off and use the Nastran values. And so I guess here, these are the default Nastran values. You can always change them, and you can even we can reset them back to default if you want. You can even if you have all your own requirements, you can even make them permanent and make a group of them. So I'll do that. And so we get 6 elements. So that's a good sign that these results match the API results. So now we're pretty convinced that the numbers in here for Nastran match the actual FO6. And then we do see that there's 2 tapers and 4 interior angle max. So, and then just to confirm, we look at both groups, they are identical groups. So that's a good sign that these are behaving how we thought they would. So now to actually go in and fix these elements. So if you go to the meshing toolbox, we can go to the surface mesh quality and contour. And let's look at the tapers first. So if we do this, we can see the 2 that failed in taper. One drawback of this particular box is that you have to kind of go through each one individually, whereas the groups are nice because the groups you can look at all the bad elements at once. But this is helpful for like doing this. For example, if we wanted to manually fix some of these bad elements, we can use this mesh locate. And if you have geometry, you could use this attached surface, but since there's no geometry, we'll use standalone mesh instead. And make sure project is on. You want to make sure you're not kind of pulling your elements or nodes out of plane to warp them. So this should be checked at all times, ideally, especially for a quad mesh. So we can go in here and just select using this white box, the arrow, to select some elements. You can shift drag to select a bunch of them, and then just click this green select button and just move it over to fix it. Okay, and you can either save or discard your changes, and then kind of same idea over here with these this taper element. It's just take a few elements, including that one we want to fix, but a couple of the neighboring ones too. And then just click on the green arrow, select, and then just move that however way you need to fix those elements. And if you run our tools quality check one more time and see how we're doing. Like we have 4 left, so let's go to, I think the other one was interior angle max. So let's flip this to angle max. Here are the 4 elements, and the reason these are failing or are warning is because we tried to force a map mesh through this kind of curved tapered region, which is the reason why I get these weird looking elements. So this time, let's try using the mesh remesh update command. And let's select all the elements in this little area here. Let's take the defaults and remesh that. So now if we do our check one more time, it looks good, all green. We can just one more time verify that we don't have any bad elements after doing those fixes. It looks like we have 0 elements now. So that's a good step in the right direction. There's just an overall kind of comment. Just because your mesh passes the Nastran check doesn't guarantee the mesh is perfect. You have to do some just visual human inspection to look at the elements yourself and see is there any area we could improve. Like, for example, a lot of triangles in here, and for stress results, often triangles are not ideal for quad meshes. So just because the elements pass, the triangles themselves pass, but you want to maybe try to max quad something else like that. And then some areas might be good to like maybe run these holes. You could do some more work, even though they pass, but still not perfect. And if you have, again, if you don't have any geometry, you could also just go to geometry surface from mesh to create geometry. And a good way to do that is using this pick by faces, and then kind of pick an element that represents maybe the big panel face. Yeah, and then click OK. You don't have to delete the mesh. And so you could go through this and maybe do this for all of them and recreate geometry that way too. But that's basically all I had for the demo. I guess one more note is that one drawback of the API is that since it reads the FO6 file, it's kind of a good thing to do in the beginning, but once you go in and actually make incremental changes to your mesh in Femap, it will no longer be connected because you'll have to, well, unless you rerun your model to get a new FO6 file. So I kind of like to use that API in the beginning, and then once I'm convinced that the API results match the initial tools, quality, check Nastran results, then I'll just use it inside Femap tools to evaluate and update the mesh accordingly. Okay, yep, that's all I have for demo.
Awesome. Thank you, Tommy. I think if you go one more slide forward, we can go ahead and open things up for questions. So thanks again, everyone, for calling in. You can unmute yourself. We have instructions here, whether you are in the Zoom application or if you're watching through the web interface. there should be an unmute button down at the bottom, which we've circled in green on these slides. In addition, you can enter questions through the chat, and we can go over those as well. So our first question is, how much error or like percent deviation can be introduced or eliminated with a good mesh? Like, is there a rule of thumb?
Yeah, that's a good question. I don't have an exact number off the top of my head. I think it's just more like the closer to perfect elements you have, the better results will be. Yeah, I guess. Do you have any like numerical values you can reference? I don't really have any off the top of my head.
No, I don't. Yeah, I don't have any hard numbers for that either.
I think for stress, definitely makes a big difference in general. I think good for spat elements. Might be less of an issue for like dynamics or thermal, but I'm not totally sure. But yeah, for stress results, it's really important. Kind of just qualitatively heavy elements. Yeah, sorry, I don't have an exact percentage number to give you.
And I guess sort of along those lines is there can be a big difference between if a poor element is like at a stress concentration where you're really interested in the stress, that's has more impact than if it's off in a corner of the model that you aren't as interested in.
Yeah, that's a good point.
So it's problem dependent, and it's also output type dependent. So whereas displacements may or may not be as sensitive to it as stresses, it varies a lot from different problem, and that's a big part of the finite element model. When you're using meshes, is making sure you not only have like good quality elements but also converge. So you want to make sure sometimes if you've got an area where element shapes visually look bad, that's why this checking is important. Is you want to build the best meshes that you can, and it can affect the results a lot for stresses or for other things, especially if the shapes are really bad. And so it's pretty important in Nastran to try to do a good job about making clean elements.
Cool, thank you, Kurt. Are there any other questions? Either you can unmute yourself or put more questions in through the chat. We'd be happy to take those at this time. Like I mentioned, we are kind of a follow-up question in the chat, sensitivity of 2D elements versus 3D elements.
So 3D elements are sensitive a lot of the same way that 2D elements are. If you imagine like a C-quad that has a bad shape, and then you were to extrude that to make a 3D element that has a bad shape, you're basically just sort of making the shape bad in all three dimensions. And so the similar kinds of stiffness errors and other errors that you might be introducing with a really bad shaped 2D element can also apply in 3D. There are some rules of thumb or things you might think about, including whether or not a particular aspect ratio is a problem for 3D elements, and for problems like composites or other things, we sometimes actually sort of size the elements a certain way to try to accomplish something. So I mean, in general, I think you got to watch for the same kinds of issues in 2D elements versus 3D elements, and not all of the checking on all the different element types in Nastran is automatically the same. And so that's where doing something simple in Femap like the Jacobian check is a really good way to check your 2D or 3D elements, since they've got a Femap specific Jacobian check that's pretty good.
And then an additional question from the chat. What errors are introduced with triangle elements versus quad elements? So
for structural problems, triangles can be very bad. They can have so like a linear triangle as opposed to a quadratic triangle can have a high error in stress. You can see a sawtooth effect kind of thing. If you've got triangles and quads, near the edge of a structure. So typically triangles are kind of stiff, and a lot of times people really like to avoid linear triangles in stress problems or structural use. Now there might be some exceptions to that where people are trying to transition meshes or do different things with the triangles. So also seeing the question about tetrahedral versus brick. So tetrahedral meshes are often a lot easier to generate, and you can get very good results with a tetrahedral mesh in structural problems. But the downside to tetrahedral meshes is if you've got nonlinear solves sometimes, or just the amount of elements you need in tetrahedral meshes to get good quality can drive model sizes really large. And so for dynamics, things like that, you can often get the same answer or better answer with a brick element with many less degrees of freedom, and the models will run a lot faster. So brick elements are very valuable in structural problems for solvers like Nastran, because you can use them in dynamics or nonlinear problems. And if the shapes are high quality, they can solve very fast and give you very good output. But having said that, there's a lot more work to make brick meshes. So, it's a trade-off. And sometimes, doing a tetrahedral mesh is fine for the particular application, like a detailed stress model that you're not going to run a lot of times or whatever. And you can get very good results if the elements are good quality. And you should be able to match results between the two different element types if you've converged and done a good job with the meshing.
Cool. Thank you, Kurt. And thank you for the great questions. We still are here if you have additional questions. Just a reminder as well that we are recording today's presentation. We should have it available on our software website and on our YouTube page, maybe this afternoon, probably for sure by tomorrow. So unless there are any other questions, thank you, Tommy, for today's presentation. Thanks, Kurt, for chiming in. And we'll look forward to talking to everyone in the future. Have a great afternoon, everyone.